negative sequence, and then finally the zero sequence one. So let me just start with the positive sequence one. Let me just copy few things so that it reduces some efforts. So starting with positive sequence network, and these are the reactances shown here. This is the system diagram. Let me put it a little bit on that side so I have more space here. So what we see here in the system, first we have two generators that are connected to a common bus bar. Generator G1 is connected grounded through an impedance or reactance that will be defined or given in this table. We will find it out from there. And then the generator 2 is connected, but it's not grounded. Then from the common bus bar, what we have a star delta transformer. One side of the transformer, this side connected to the bus bar, is star connected and grounded through a reactance or impedance. The other side is delta connected. Then we have a line for which we also have the reactances shown here, x1, x2 and x0. And then we go to the next transformer T2. Again, it's connected in star delta configuration. The star side is grounded through an impedance connected to another bus bar where there is another generator possibly coming from another power station, for which the star connection is grounded solidly. It's defined as a generator, as the generator G3. So we'll start with the neutral bus. So neutral bus is labeled as N1, as we know. So we need to just extend this line, these drawings in Microsoft PowerPoint. So what we need to do, I need to just copy a reactance from here, paste. So what we show here, the first generator is coming with a voltage source shown as E1 with the polarities. Negative is going to go to the neutral bus and positive is towards the load side. So that voltage source is shown. Then we have the generator 1 positive sequence reactance x1 is shown. So we turn with the generator 1. Now when we're done with the generator 1, we go to the generator 2. For generator 2, what will happen? It will be the same thing. So it will also have a voltage source. It will have its own reactance as well. So if we can show it this way, so we'll say the voltage is E2, and actually when they operate in synchronism, actually it becomes same. E1 is equal to E2 is equal to E, because they are in turn connected to this common bus bar. So what we see, these two generators are connected to this common bus bar. We have shown the positive sequence reactance along with the voltage source. Now we have to connect these two generators to this common bus bar. This is this bus bar that we see in our system diagram. This is the common bus bar where the generators are connected. Is that clear to everyone? Please let me know. You can show some text or some symbols, or thank you very much. Many of you raised your hands. Now we need to go to the transformer and the line, then the second transformer, finally reaching the other bus bar, and then go to the third generator G3. So the next one is the transformer. So we just extend it to a line. It does not represent anything in terms of reactance or impedance. So now we need to put that transformer, and we know when we have transformer, we always draw it. Oh, sorry, this is positive sequence network. I don't need to copy anything. So for transformer, So we need to show, I need to correct this a little bit. This need to be x1 of G2, and then this is the x1 of the transformer 1. So it will be transformer 1. So we got the transformer 1, and when we got this, what we now need to do, we need to go to the line. So line has a reactance. We look at the table. If it is showing any reactance, then we need to show it in our sequence network. If there is no reactance, meaning we neglecting or ignoring the reactance of the line, like this portion, the one I selected just now, does not represent any reactance. All other reactances are shown as reactance. So the next one is the reactance of the line. So I can copy this one and paste it to this part and show it as the line positive reactance. So it will be L1 and the X1 is the positive reactance of the line 1. It's labeled as L1 on the table and the system diagram. We must use the same label. So line is done. Now we need to go to the transformer. So what we can do, we can copy this and connect it to the line reactance. They are in series, must follow that part. So this is the transformer 2 positive sequence reactance. That's why it is X1 of T2. So we have done the transformer, and we arrive at the bus bar. So we can connect the transformer to the bus bar like this, and then what we have a generator connected to that bus bar. And for generator, what we always start with, we start with the neutral bus, because the generator is always connected to the neutral bus. So we can draw the neutral this side, or we can use this neutral bus, extending it, and show the generator here like to the other two generators. Let's do it this side a little bit different, just because we need to know all other ways people used to follow, because if we follow one style, we might not know that the other people are also using the other style. So this is the third generator connected to the neutral bus, and its voltage source is shown as E3, and then we show the polarity of that voltage source, and then we show the positive sequence reactance X1 G3. So we got that transformer, and that is actually connected to this bus bar. So what we can do, we can connect that to the bus bar. Let's connect it this way, or you can do it from the other side if you want, like looking like the one that we see on our system diagram, so that we don't get confused. But if you drew it from this side connected to this bus, it's also correct, because there is no problem with that. So is that okay? Everyone got it? Just let me know when you are 100% sure of how we have done it. And sometimes the diagrams look a little different, because like this one, I drew the neutral bus vertically for all of them so far. I could draw it horizontally as well, and then the system sequence network diagram will come down vertically as we go along, from the generator to the transformer to the line to the second transformer to the last bus bar and the generator. But in electrical point of view, they are all same. So we can now go to the negative sequence network, if that is okay with you. So negative sequence network, what we'll have to do, this will be N2, the negative sequence reference bus. So it's N2, and for negative sequence reference, we don't need any voltage source, so they have to be now removed because I copied and pasted, so I have to remove. But for you, you don't need to draw them at all. They are not present in negative sequence network. So for negative sequence network, we're showing the negative sequence reactances. So this should be x2 of G1, x2 of G2, x2 of G3, then x2 of the transformer 1, x2 of the line 1, x2 of the transformer 2, and all other connections remain the same. So that's the negative sequence network. Is that clear to you? Please let me know when you have drawn this on your book so that I can go to the next slide, because you won't be able to see it, and this slide, the amount of space available is not going to allow me to draw the zero sequence network. So are you done with this negative sequence network and understood it? Okay, let's go to the zero sequence network. So for zero sequence network, what we again start with, we start with the generator 1. So generator 1, what we have, the generator 1 is also star connected, grounded through a reactance. The reactance is given here Xn. So what we need to do first, we need to show that, and then we need to label it as its value. So what will be there is the 3 times the Xn of generator 1. Then we need to have its own zero sequence reactance. So what we do now, that is now need to be shown, because it's connected through so that's the generator 1. Is that clear? Don't worry about the other drawings, I'll correct them as it comes. Just imagine that they are not connected. So that's the part that we have completed. Generator neutral reactance Xn times 3, it always appears as multiplied by 3 on the zero sequence networks. Then we show the generator zero sequence network. So that generator 1 is done. We can come to the generator 2, show its zero sequence reactance. So it has no impedance connected, so it just only the zero sequence reactance that will be present here. So X0 of G2, and if you remember, when we have the star connection, delta connection, we always start with something, we keep an open here to check, and then finally we will connect them. So I keep this open, this is for the generator, and then generator G1, and we have to do the same thing for the generator G2. So let me just do this quickly. So generator G2, we leave the open, and then we look at it, and then we can do the generator G3 as well, and we can label it as X0 G3, and we look at the star connection and it's grounded, but it doesn't have any impedance, so it will not have any 3xn kind of thing. So we have these three opens after the generator terminals. So what we now need to do is look at the connections, and then we close or leave them open. So first, generator G1 star connected, grounded. So what we do, we close that one, because star connected, grounded will allow us to, so that's the, let me change the color to red so that we can see we closed it because it's star connected, grounded. For the generator G2, it's star connected but not grounded. It doesn't allow zero sequence current to flow, so we cannot close it, so we leave it open. We look at the generator 3, it's star connected, grounded solidly, so it will allow the zero sequence current to flow, so that's why we close it. Okay, so that's done. Generators, even the generator 3 is done. Now we can come to the common bus bar. So common bus bar now needs to be shown. So we arrived at the common bus bar. Now after bus bar, what we have a transformer. So when we have transformer, we need to do this kind of things. Let me, oh sorry, it's not gonna help. Let me just copy this and paste it here. Let's see how it looks like. Ah, goodness. Ah, it's even worse. So that's the bus bar. That point was supposed to be here, and from the bus bar we have this transformer connection. We could possibly lower it a little bit. Yeah. So what we now need to do, we need to connect it to the bus bar. So that connection is done, showing the X0 of T1. And let's forget about these lines. For now, 4 of them are opened. Also, don't worry about those. I will check with those arrows for the determination of equivalent reactance if you want to do that. So X0, this one I forgot. This is supposed to be N0. You must make sure that all the labelings are correct. So this now transformer end connection now needs to go to the neutral of the system. So it goes to the neutral of the system, X0 of T1. We look at the connection, and what we find that it also has impedance transformer 1. So what we need to do, X0 of T1, and along with that it will be 3 times Xn of T1, because it will be in series like this case, so we can show them as one reactance and represented it as a combination. So it's the total of the reactance between the neutral and ground, and the zero sequence reactance of the transformer. Reactance of neutral and ground will always appear multiplied as by 3. So that's what we have done. And then this primary side, this side is star connected grounded, so this switch now needs to be closed, and it's not delta connected, so we leave it open. We go to the other side, it's not star connected grounded, so we leave this series switch open. It's delta connected. What we need to do, we need to close this switch. So that's the transformer 1. Is that okay with everyone? Please let me know if you understood it.
So can you please explain a little bit how are we close? Why are we closing the parts on the left and the right side of the transformer?
If the star connected grounded, then we close it. If the winding is star connected grounded, then we close the series switch, the ones that you see horizontally at the moment.
Okay.
And if it is delta connected, then we close the shunt switch like this. But if you rotate this drawing, then it will look different, but it will still be the same. Let me just do that. If I can show what will happen, if, like I was telling, that it might be drawn vertically or horizontally, but if someone drew, goodness. So if someone drew this diagram like this, it will still be the same thing. These are the series switches, these are the shunt switches. This part will be connected to the neutral bus. Is that okay?
Yes, sir, it's okay now.
Okay, so I keep it here as for an example how we might have a vertical and horizontal way of drawing. They are same. So that's the transformer 1. After transformer 1, what we have a line, the line impedance. So the line impedance is shown here. We can line, so x0 of line 1, it has to be x0 of line 1. We show the line 1 here, then we go to the next transformer. So we'll have to copy this whole thing and label them accordingly as well. So we go to the next one. Let's leave these switches open in the beginning, and of course we'll have to make sure that this part again goes back to the neutral bus N0. So we extend this line, connect it to this transformer, and it's connected here. So that's the neutral bus connected to the transformer. So this one also has xn, but it's T2 x0 of T2. Now we need to check this side is delta connected, which is this side. So we close this shunt switch of this side and done with this side of the transformer. We can go look at this side, is star connected, grounded, so it will be closed on the series switch, not the shunt one. So that's that one. So the transformer is now completed. T2 is completed. So after transformer, what we have the bus bar. So we can show the bus bar, and it connects to the generator G3. What I was copying. So that's the bus bar, and this bus bar is now connected to the generator G3. Sorry, this portion is not connected here. This one is like that. So now I can connect this one. Let me redraw it so that it doesn't overlap much. Let me just redraw it here. Oh goodness. So that is now connected to this bus bar. Sorry for, you will have to change the diagram a little bit just to make sure that we don't want to jump. You can jump, no problem, but we want to avoid if it is possible. In this case, it's possible to avoid any jumping the lines. And for this case, you could draw it from this side as well. Like I said, you can draw it from the way it is shown in the system diagram. Let's do that. It's the same thing. So generator G3, now we have done it earlier, so that's the complete zero sequence reactance diagram or the zero sequence network. But again, this doesn't show the fault point on the system, but you can think of any fault maybe on the line or on the bus bar, either of these two bus bars, and determine the equivalent reactance, checking in which way you can arrive at the neutral bus starting from the fault point and how many ways of are there, and then taking that circuit series parallel combination into consideration. Is that okay with everyone? Let me give you 1 minute to absorb this section, what we have done with this one.
Sorry, sir. Once again, can I ask a question?
Yes.
I'm lost. I didn't quite get you. Why didn't we close the series connection in the generator 2?
Look at the generator 2 connection, how the generator 2 is connected. What is the connection of the generator 2? Look at the system diagram given in the problem. Tell me what connection you see there.
It's the Y connection, star connection.
Yes, and after that, is the neutral point grounded?
No.
If the neutral point of any star connection is not grounded, it does not allow any zero sequence current to flow in the phase or lines that we have studied long ago in the theory. So you need to now just go back there if you forget why.
Okay, thank you.
For now, we just know that if the star connection is not grounded, it does not allow any zero sequence current. We're talking about zero sequence current because this is the zero sequence network that we are considering and drawing. So zero sequence current is not flowing in the phases or lines of a star connection. That's why it is left open. Whereas if you look at the other two generators and even the transformer, they have star connection grounded. That's why the switches are closed for generator 1, G1 and G3.
Okay, thank you, sir.
So can you go to the next one? Please let me know if I can go to the next one. Can I? Thank you very much. So the next one is something similar but a little bit different. So what it says for the power system shown, and this is the power system what we have generator G1, its MVA rating is given. Now that's how these things are a little bit different. We considered XN, it was given in per unit, but now we have in ohm. J3 ohm is reactance. J3 ohm is reactance. So generator star connected, grounded through that reactance of J3 ohm, and generator G2 is star connected, again not grounded. Its MVA is 1.5. It's connected to a transformer of 1.5 MVA. This side is delta connected. The busbar side is star connected and grounded solidly, coming to the power station busbar, from where we have a 6 kilovolt cable labeled as C1 coming to another busbar at a substation, and to the substation what is coming there from the infinite bus, which is also called grid. There is a 70 kilovolt line which is labeled as L1 coming to another transformer connected in delta and star. Star is not grounded. Its MVA rating is 3 and labeled as T2, coming to the substation bus bar where there is a fault point shown. So what it is asking us, calculate the impedances of all the equipment in the system in per unit based on common base of 6 MVA. That's what we have done in power systems 1. So can you do this part and tell me the answers first? Then I will go to the next part, which is drawing the sequence networks. So first part A is obtaining the per unit impedances, because some of them are not in per unit, C1 and L1. Not only that, these equipment now are given with their corresponding MVA ratings. So we will have to consider that. Can you do this calculation and tell me the answers for those? So you will start with generator 1, you will go to generator 2, you will go to transformer 1, you will go to the 6 kilovolt cable, you will go to the transformer T2. You will have to calculate the reactances for the 70 kilovolt overhead line. Sorry. So if we start with the solution, but the calculation is to be done by you. Make sure that you have your calculator. So the first one, what you will calculate, x1 of g1, x2 of g1, x0 of g1, all should be in per unit. Then you will calculate the same thing for, sorry, then you will do it for the generator 2, x1 of generator 2 g2, x1 of, sorry, x2 of g2, x0 of g2, and then you will do it for the transformer, x1 of transformer 1, x2 of transformer 1, x0 of transformer 1, and then We'll have to do it for the others as well. Let me copy and paste it there. So what is next there is the cable. So x1 of cable C1, x2 of C1, x0 of C1, x1 of the transformer T2. So T2, T2, T2. Then we have to consider the line 1. Line 1 is L1 and that's the level. So you now calculate and tell me the values of these one by one. Start with the generator 1. Remember that common base is given. Base MA is equal to 6. That's given. Times base MPA over actual MPA. Now you must calculate it and tell me. Don't waste time, please. It's now becoming challenging to
All the answers for generator 1 will be the same as what's in the table.
Who is this? Timira.
Yes, sir.
So it took like a 1 million of light year to say this. It shouldn't have taken even a second. So what's the value? Is 0.28, 0.15, all are in per unit, and 0.09. Everyone got it now? So calculate it for G2 and tell me quickly. But if you don't want to do this calculation on your own, you will never understand and learn, and you will achieve your aim and objective to take the answers from others. And these days it's easy with computer, camera. Take a photo, take a snapshot, snip, copy, paste. That's easy, and you will be very good at that. And there is no doubt about that. So what's the values? What are the values of x1, x2, and x0 of G2?
I'm guessing 0.88 for G2, for X1 G2. I'm not sure it's correct.
Why is it you are not sure? You are a fourth year student. Next year you will call yourself, or before next year even you will call yourself an engineer. Huh? Why are you not sure?
I'm not sure whether the value I read there is 0.22 on G2 X1.
If you are not sure, then the people who will be thinking of giving you a job or employing you will not also be sure whether they should give you or employ you or not. They will also not be sure at all. That's what is going to happen. I told you probably that one of our students don't have a job, and the reason is that he managed to get a training. After the training, he was told that you are encouraged to find a job somewhere else. Those people are very gentlemen. They don't say that we fire you or you don't need to come from tomorrow. They're saying they are encouraging to find a job somewhere else. So that's what they do. So x1, x2 and x0 of G2 is done. Timira, thank you very much. Next one is the transformer one.
Getting 0.08 for X1 T1.
Check it.
So all will be 0.2.
Yes. Thank you very much. So it will be 0.2, 0.2, 0.2. So that's transformer 1. I'm not writing PU. So if we're done with that, we can now go to the cable 1. How do we calculate the cable reactance? We calculate them if they are in ohm, then we need to write the formula is X in ohm times base MVA over kV squared. So X in ohm is given in this case. Base MVA we know, and kV squared. kV we know, we need to look at the kilovolt, which is mentioned in the system diagram. Because it's given in ohm, it's not in per unit in the first place.
I'm getting 0.12 for X1C1. I'm getting 0.12 for X1C1.
4.12.
Yeah, or 0.108. I rounded off to 0.12.
You have no right to round it off. You must know this.
Yeah, so it's 0.108.
That your final answer will be very, very off from the actual value.
Okay.
You have right. I actually did not mean that you have no right. You have right to round off to whatever. You can say 0.12 is 0.1. You can do another rounding off, and 0.1 you can round off to 0 as well, no problem. But what will happen in the end, because this is only the first step, we calculating the reactance, it will go to the reactance diagrams, it will go to the fault calculation, it will go to the voltage calculation, it will go to the power calculation. They will be very, very off. Like, I don't know if I gave you this example, like we always consider 2 decimal point, 2 digits after the decimal points when we deal with money. Am I right? Like 100 cents, 1 rand. But if you imagine of any product that is sold on each and every day, and if you go to the 3rd digit, how much you will earn or lose. That's why some of the products actually has more digits than 2. I can give you an example like petrol or fuel. It has 6 digits, 7 digits in some countries. So x1, okay, I wrote it in wrong place. x1 is 0.1083, x2 C1.
Would be the same. Should be the same.
Singayo is writing what is actual MBA of what? Actual MBA is written there on the equipment. Actual MBA is the actual MBA rating of the equipment, motor, generator, transformer. Actual MBA is the actual MBA rating of the equipment, like for example, motor, generator, transformers.
No, sir. I wanted to ask, is it like a value or
Yes, of
because I
course.
couldn't see it?
In which year you are? You are in fourth year. This question doesn't make that much
No,
sense. Honestly, it tells me that you are not in
no,
the system. You know what?
no,
Okay.
no, sir. It could be that I can't see properly on your slide.
Why you can't see the slide properly? What is wrong? You are using a phone.
Yeah, I'm using my phone.
It doesn't help. If you are using a phone, it might be you are right that you can't see it properly. You should use
Yeah.
computer.
Okay.
Where are you? You are not at home or not at study center or on campus.
No,
Are you on campus?
no, sir. I'm at town.
So it's your lecture time. Why are you on town? In town?
I'm here at the doctor.
Oh, okay. So sorry.
Yeah.
Get soon. Yeah, maybe if it's a cell phone, you cannot see it clearly. But actual MBA is a value that is the MBA rating of the equipment, motor, generator, or transformer. So
Okay.
now we need to know the value of x2 of C1, x0 of C1 immediately. Cannot wait anymore.
It will be the same value as x1 c1. Should be the
Which
same
that?
value as x1. Should be the same value as x1 c1.
Yes. And then x0 of C1.
0.155.
Yes. Everyone got it? Can we go to calculate the reactances of transformer T2?
0.3.
So they're all 0.15.
T2
They'll all be 0.15.
0.15. 0.15, 0.15, 0.15. So we're done with T2. Now we need to go to the line 1, L1, that is operating at 70 kilovolt, and its reactances are given in the table, but make sure that you take note of the unit. It's again in ohm. The reactance of the line 1, which is operating at 70 kilovolt, its reactances are given in ohm, not in per unit. So if it is given in ohm, we need to use that formula, x ohm times the base MVA over kilovolt squared, and then you can find the values.
So x1 and x2 will be 0.104.
0.104.
104.
Yes, that's perfect. Actually 1041, I don't even leave that one out. According to my calculation is 1041, and that is also x2 because it's also 85 ohm, 0.1041. and x0, I don't know why I wrote it small l, sorry about that.
Sir, and x0 will be 0.1408.
Yes, exactly, that is the value 1408. 0.1408 is the value for the zero sequence reactance of the line 1. Now what is outstanding is the reactance of the connecting wire between the star point of the generator winding and the ground, which is given as 3 ohm in the system. It's not in the table, it's still in the diagram, and we need to calculate that one. I wrote it here, xn of g1. So what will be its value? And we need to know that because it will come in the zero sequence network when we will draw it, but in the zero sequence network it has to be multiplied by 3. Just I'm repeating for you. So x ohm is given 3 ohm, base MVA we know, and the kilovolt at which the generator is operating we know. What's the voltage of generator? G1. Sibusiso, 70 kV line or 7 kV line? Are you using a cell phone or a computer? Can you not see it's written on the line? Look at the line where the line is. I'm pointing it. My mouse pointer is above the line where it is written 70 kV or 7 kV. Did you find it? Okay, thank you. So anyone has the value of xn of G1? It should not take so long to tell me the value of X energy. Yakari, Timira, Luvo, what is happening? Point 0.5 per unit. Anyone else got any value? All the reactances are now in per unit. You must make note of that. I did not write the units. We should write it all the way. Everyone got it? 0.5. Okay, thank you very much. Can I say that you can do this part, drawing the sequence network? Can you do this part yourself? Because we did quite a few examples. Can you do this part by yourself? If you have any doubt, you can share your screen and show it. Before you want to do that, you can ask me. Can you do this sequence networks drawing by yourself? And Singwaya, you can't do it by yourself. Why? Can you explain why?
So I think I need some more examples to kind of get a grip of it. But I don't think I'll be able to do it on my own.
Okay. I listen to what you're saying that you need more example, but I think you don't need more example. I think what you need is to study. And you need to be in the system, and this is a very good example of that you are not in the system. And when I say that you are not in the system, means you're not involved or engaged with this at all. What you need to do is you need to study, and after that you can definitely be drawing this without any problem. But if you still cannot manage, please let me know. So I ask you to draw this and show me the drawing on your screen, sharing it. You can, what you can do, you can draw it on your book and just take, maybe show it in front of the camera, or you can even convert it to PDF like the way you do and share it. Anyway, I just need to see the diagrams of the sequence networks.